So I wanted to go ahead and actually review the stuff that we covered on Friday in class. So we studied two major topics. The first topic is projectile motion, and the second major topic is forces and free body diagrams. That's really how I would say it. So to this end, I really want to just kind of summarize the results rather than talking about where every single thing came from. So when we deal with projectile motion, the idea is that we are given something that we launch into the air, and there's a couple rules. So I'm just going to kind of draw the ground here. And what we want to keep in mind is that we're launching an object. It's always got a given initial position and an angle that we launch at. And there's essentially three things that we want to know about the object. We want to know its height, we want to know its range, and we want to know the time it's spent in the air. So again, height, range, and range is really the horizontal distance it goes. Height is the maximum vertical height that it achieves. Time, t, specifically another word for this is the hang time. And that doesn't mean the time spent floating. That's impossible. Things don't float. If we factor air resistance in, yeah, but we're assuming that the thing is massive enough that air resistance doesn't matter. It's either going to be rising or falling, and that total time spent in the air is the hang time. And there are three key formulas that we came up with. Now, we went through a full derivation of these formulas. We're not going to make you do that on an exam, but the formulas we use. This is the formula for the height. And let's remember that g is going to be 10 meters per second squared when we're doing quizzes and tests, or 9.81 meters per second squared when we're doing labs. Now the time spent in the air, that's going to be the following. And let me just double check that. So v naught sine theta. Yep, that's it. And for the range, the horizontal distance, that ends up being v naught squared sine of 2 theta divided by g. There's a little bit of trig involved there, so we're just going to use the formula. One thing I want to point out, if they ever ask you how to get the maximum range for a problem, there's a little bit of trig here that we can do. The sine of 90 is 1. That's the maximum possible value for a sine function. So if you set theta equal to 45 degrees, that's when you're going to get the biggest value of r that you can possibly get. Just a little aside there. So we basically covered that for projectile motion. We did a little bit of practice, and just to remind you, for projectile motion to be true, you actually have to start and land at the same elevation. Here's the formulas again right here, just to kind of remind you. And from there, we launched into a discussion of Newton's laws of motion, and we had three ideas that we took a look at. Now, those were incorrect ideas, and I've got the video in Haiku if you want to rewatch it. Truth is, though, what we're going to really do is get a clear definition of forces and how they affect objects, and then we're going to go back and re-examine some of our old ideas, again, under a little bit more of a formal lens. But here's the basic ideas that we started with. We started up with the idea of what is a force. And what we concluded was a nice, simple definition, thank goodness. As far as we are concerned in physics, a force is a push or a pull. And the intended effect of a force, the effect of a force is to speed an object up, slow it down, and we're going to get into this one later on, it also turns out that if you want to change an object's direction, that also requires the application of a push or a pull. So these are the three things really that forces do. They speed you up, they slow you down, they change your direction. And again, getting an object moving is a case of speeding it up. Stopping an object is an example of slowing it down, so that's why I didn't include those two in this example here. And then we watched a little video on what are the forces on you, and of course we had our little Canadian dude living in Australia. And we made it clear that when you want to represent the forces on a person, we do two things. And this is kind of what I'll call the basics of free body diagrams. And the abbreviation is FBD. We use that in physics, and you'll see it in some physics classes. And again, what we mean by a free body diagram is how we draw the various forces on things, the various pushes and pulls acting on objects. So we had the sketch of the person like this, but this is not what we do to actually draw forces. We represent the person as a point, and this point represents the center of gravity or center of mass of the person. Now we know that there's a downward gravitational force from the earth pulling the person. And what this video suggested with the little toy and the little spring pushing up, if I've got a person standing here, is that even the ground applies sort of an upward force that keeps us from falling through to the earth. Oh no. So that's what doesn't happen, just to be clear. That force, that upward force from the ground, is called the normal force. And because these two forces are balanced, because they're equal, we neither sink into the earth nor do we jump up into the air. And we draw congruency lines just like we do in geometry class. So, just to label, Fn is called the normal force. Fg is called the gravitational force. And from here, we went into practicing drawing free body diagrams. But I wanted to say a couple things. And we drew the free body diagram on the boxes, and we talked about when something moves in the air. So if I throw a ball into the air, okay, so the ball is thrown, and there's no air resistance. The point is, when you draw that free body diagram, you only have the downward force of gravity. That was the big point. So a lot of people want to have a force of throwing, and that's just not true. There's only the downward force of gravity. Now, to get the ball moving, there absolutely is a force of throwing. But once I let that ball go, there's something else that keeps it moving that we're going to get to on Monday when I bring in some toys for us to play a couple little games. So, when we actually dealt with free body diagrams, there were a number of forces that we named. And I'm actually going to skip ahead to the slides so that we have them here. So we actually went ahead, and these are the forces that we deal with, that we use in physics. We're going to introduce two more forces later on. So this is going to be in week 2. Actually, I should call it week 3. Next week is going to week 2. In week 3, we're also going to talk about an electric force and a magnetic force. I know it's weird to call it B. Trust me, magnetism gets a little obnoxious. So we've got magnetism, we've got electricity, and on the very last day of class, when we deal with atomic physics, we're going to deal with Fs, which is something called the strong nuclear force. We'll never see this one in free body diagrams because it acts on such a small scale that the physics that actually describes how it works doesn't lend itself to the use of free body diagrams. That's how I'll say that. So we talked about weight and the force of gravity being interchangeable terms, okay? And this is different from mass. So we're going to have the usual physics class struggle of distinguishing between mass and weight. And we're going to be doing a lot of labs in the morning, kind of a big lab activity in the morning to kind of distinguish those two things. M is the normal force, is the contact force on a surface. I'll write it as N, or you'll see me write it as F with a subscript N as well. And then basically what we did is we spent some time drawing free body diagrams and getting things labeled. We did a free body diagram for this situation here. So we have big M and we have little m. And the way we drew these free body diagrams, we had the normal on big M, we had its weight. The rule for tension is that the rope force always goes out of the object, away from it. And the other thing is, in this case, these two tension forces, because it's the same rope and it's connected, they're congruent, they're equal forces. And then we have the Fg down here for this little m, its weight, its gravity force. I'm going to do one small thing. I want to distinguish my big mass from my small mass, so I'll write a little superscript there in parentheses. That's not a power. I'm not raising it to any power. I'm simply saying, hey, this is the force of gravity on the big dude, and this is the force of gravity on the little dude right here. So that's pretty much all of the new stuff that we covered on day 3. And then if you remember, we broke for lunch, I returned your quizzes, and then we took the exam. And I will be grading those later today. Sorry, no news to report yet. As of now, it is Sunday, June 11th, 9:40 a.m. as I'm recording this. So I will be posting grades on that exam later today.